Okay, so today we are going to continue talking about Newton's laws, except today we're going to focus a little bit more on gravity. We've started talking about it a little bit yesterday, or not yesterday, but a few days ago when you guys were doing the lab on the website, we had to use gravity. We kind of already alluded to gravity and we already talked about what the acceleration of gravity was. But today we're just going to get a little bit more specific as to what gravity is. So first of all, okay, gravity is an attractive force between any two objects. What does attractive mean? An attractive force between two things. What does that mean? They're being pulled towards each other, right? Doesn't mean attractive as they look nice. It means attractive as they are being drawn to each other. Okay, kind of like magnets are attractive forces, they stick to each other. Okay, this force depends on two things. It depends on the mass of the objects and the distance between them. So the closer two attractive forces are to one another, the stronger the pull. The farther away the two objects are from one another, the weaker the pull. So like for instance, if you think about the sun and the earth, isn't there a pretty big distance between the earth and the sun? Yes, which is why we are not moving towards the sun. We're kind of at a perfect distance. We're far enough away from the sun that we're not being pulled towards it, but we're close enough to the sun to keep us in an orbit. So we're kind of in a nice happy medium. Okay, so gravity increases as the mass increases or as the distance decreases. So gravity, the force of gravity will increase by two different ways. If your mass gets bigger or if your distance gets smaller, your gravity is going to increase. So if my gravity is decreasing, the opposite is going to happen. My mass is getting smaller or my distance is getting greater. So that, therefore, the attractive force between the sun and Jupiter is probably less than it is between us and the distance, or us and the sun, just by looking at distance, correct? Jupiter is farther away than we are. Okay, it's also probably more massive, but we're just looking at distance right now. So, only Earth is close enough and has a large enough mass that you can feel its gravitational attraction. The sun is too far away, so we don't feel a gravitational attraction towards the sun. If we felt a gravitational attraction towards the sun, we'd probably start floating towards the sun, but we don't. We float towards the Earth, correct? If you jump up, don't you fall back down? Because you are feeling the gravitational pull of science. Your textbook sitting on your desk, none of you have a textbook sitting on your desk, but if you had a textbook sitting on your desk, would you feel a gravitational pull towards your textbook?
No.
Probably not. Why? Because it doesn't have enough mass. Okay, so gravity is one of the four basic forces that also include the electromagnetic force, the strong nuclear force, and the weak nuclear force. So we're just talking about some different types of forces here. Okay, gravity also has a long-range force that gives the universe its structure. Gravity is a long-range force. What do you think that means? Long-range force. It works from a very, very, very big distance. If you go up to a very high altitude, if you climb a mountain, are you still under the effects of gravity? Yes. Have you increased your distance up? Yes. Are planes under the influence of gravity?
Yes.
Yes. Are they very high up? Yes. It is a long-range force, which means you have to travel a great distance to overcome the force of gravity. I mean the moon. Think about how far away the moon is. The moon is being affected by the Earth's gravity. Okay. Nuclear forces act on the nuclei of an atom. So when we're talking about atoms and we're talking about the nucleus, a nuclear force is what keeps an atom all together and working properly. Electromagnetic forces, this is when we're dealing with electricity and magnetism. This is when we have chemical reactions, so on and so forth. Okay, so let's talk about weight a little bit. Weight and mass are not the same thing, correct? Weight and mass are not the same thing. So, when in this class, you need to kind of take a step back. When you're, especially on a test, when you're doing a short answer question, if I ask you what 30 grams is, you need to take a second to figure out if I'm asking you the weight or if I'm asking you the mass, because they're actually two completely different things. Weight is the gravitational force on an object. So weight, when I tell you my weight, I'm telling you how much force gravity is pulling down on my mass. Okay, weight has to take into account the whole idea of force being pulled down on you. Even if you are not falling, the force due to gravity's earth is still pulling you downward. Okay, if you are standing on the floor, the net force on you is 0. So I'm standing right now, or I'm sitting actually. As I'm sitting, is gravity not pulling me down? Gravity is always pulling me down. Am I falling through the floor? Am I falling through my chair? No, so there has to be another force, because if you are not moving, your net force is 0. So there has to be another force acting up on me to keep my net force 0, to keep me from falling through the Earth's surface. Okay, whether you are standing, jumping, or falling, Earth exerts a gravitational force on you. And the gravitational force exerted on an object is called the object's weight. So, mass is how much matter you contain. Weight is how much force is being pulled on your mass. So I have mass. Is my mass going to change whether I'm on the Earth or the Moon or Jupiter? No. What is actually changing? Your weight, the force being pulled on your mass. So, sorry, did I go too fast? All right, due to inertia, what's inertia again? Uh-oh, we've slept since Newton's first law. What's inertia? Inertia is an object's inability or a resistance to change, right? So if something is moving, it wants to keep moving. If something is at rest, it wants to stay at rest. That's what inertia is. It's an object's wanting to stay in its current state of motion. Okay, so due to inertia, all objects fall with the same acceleration regardless of mass. So on your notes, I want you guys to star, circle, make lines, highlight, color code something, this statement right here, because this needs to be memorized before your test. I am not going to give you the acceleration due to gravity. I'm not going to tell it to you. I'm not going to write it on the board. You need to have it memorized. So, in other words, what I'm saying is right now on your paper, if I was taking notes with my pen, I would go, ooh, she said test question. I'm going to make it a pretty color. Ooh, let's make it red so I remember it. Ooh, test question. Ms. Tackett said this is going to be on a test, and she is not going to tell me. I need to remember that the acceleration due to gravity is 9.8 meters per second squared. So when I give you a force equation and I say a 12 kilogram object is falling due to gravity, what is its force? You're going to go, oh, test question, Ms. Tackett said acceleration due to gravity is 9.8 meters per second squared. Never, ever, 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 ever changes. Okay, this is considered the gravitational acceleration for Earth. Okay, so let's see if we can do some math practice. Let's see if we can use this with our formula. So, if you remember the other day, we started talking about Newton's second law. Newton's second law says force is equal to mass times acceleration, or acceleration is equal to force divided by mass. And we learned how to write the T-chart, right? We said that our force goes on the top, or we've done force equals mass times acceleration, or we've done acceleration is equal to force divided by mass. You can rearrange the equation as many times as you want to, but it all says the same thing, correct? And this is Newton's second law, correct? Just kind of review from what we did the other day. So, let's now compare his second law to the idea of weight. Well, we know weight is a form of force, correct? Because look, it is measured in newtons. As soon as you see newtons, you should go, oh, force, Newton, force, Newton, force. Okay? Mass, gravitational acceleration. So aren't we doing Newton's second law? What's the difference? We're doing Newton's second law, but what's the difference? This time we're doing weight instead of net force, but weight is a type of force, so it's still force, right? And this time, we don't have acceleration, we have gravity. We have gravitational acceleration, which we can shorthand using G. Oop, I kind of covered it up instead of highlighting it like I was supposed to. But you see G down here. G stands for gravitational acceleration. Their unit for acceleration is still meters per second squared. I'm giving you Newton's second law, am I not? Isn't this the exact same equation for Newton's second law? The only difference is we're dealing with gravity and we're dealing with weight. Nothing else has changed. We're going to do the exact same practice. So, let's look at an example. The acceleration due to gravity on the moon is 1.6 meters per second squared. Therefore, a person would weigh only about 1/6 as much on the moon as on Earth. Well, let's do a little bit of practice. Let's pretend we all weigh 10 kilograms. That's probably far-fetched. But we all weigh 10 kilograms. We all know that the acceleration due to gravity on Earth is 9.8, correct? So that means on Earth we're going to have a force of 98 newtons, correct? So let's compare that to the moon. So the moon, and I'm going to write it down here so we have room. If we still weigh 10 kilograms, we're not going to times it by 9.8. We're going to times it by 1.6. So on the moon, we're going to have a force of 16 newtons. Do we still have the same mass? Yes. The only thing we changed was the acceleration. So as a result, a person would weigh only about 1/6 as much on the moon. So let's see. To find our fraction, we're going to do 16 divided by 98. If I put that in my calculator, I get 0.16, which is about 1/6. Okay, so all we're really doing when we're comparing the forces. The force on the moon should be less than the force on the Earth. We see this when we see astronauts. When the astronauts jump on the moon, don't they float up a lot higher and don't they come down a lot slower than they do on the Earth? That's why. Okay, so let's continue to talk about gravity. You've probably seen pictures of astronauts and equipment floating inside the space shuttle. Well, looky there. I got ahead of myself, didn't I? Any item that is not fastened down seems to float throughout the cabin. However, they would still have a weight due to the force on gravity because unless you go out farther than the moon, you are still under the effects of gravity. So why do things float in space? They're still under the effects of gravity, except our distance from the Earth is increasing, so we feel less effects of it. We're still under it. That's why they're not floating away out and out and out into space. They're still under it. They just have a greater distance, so they don't feel as much of the gravitational pull as you do when you're on the surface of the Earth. This is why when you guys have probably gone underwater. Most of you have probably been to the ocean. I don't know if anyone's ever gone like deep sea diving, but as you go down, you feel like you're getting heavier and heavier and heavier because you're yes, the weight of the water on top of you, but you're technically going farther down to the Earth, so the pull of gravity is also getting heavier. So it's kind of lots of ways to look at things, right? Okay, so let's talk about floating in space a little bit. Why do objects seem weightless in orbit? Well, we've talked about free fall a little bit, right? And we talked about the moon orbiting the Earth. Well, and things in free fall are supposed to be falling towards the surface of Earth, but are we standing still? No, the Earth is constantly moving. So yes, the moon is trying to orbit us. They're orbiting us, but at the same time, they're actually trying to fall into the Earth because they're under the effects of gravity. Doesn't gravity pull things towards the surface of the Earth? Yes. So, but as soon as the moon starts to fall towards the Earth moves. So it's almost like it's constantly going in this series of I'm trying to fall into Earth, but the Earth keeps moving. So is it falling? Technically, yes. Do we see that? No, because we are continually moving. That is why it is orbiting the way it is. All right, so let's talk about some projectiles. So when I'm talking about projectiles, it's kind of like if you're shooting a bullet from a gun, or if you shoot cannonballs from a cannon, or if we're using a slingshot, throwing things, not exactly, yeah, but you won't see it as well because you can't get as much distance when you throw things. But projectiles have horizontal and vertical velocities due to gravity, and they follow a curved path. So when you throw a ball, like a pitcher, the force exerted by your hand pushes the ball forward. So you are pushing the ball out in front of you. This force gives the ball a horizontal motion. So it is moving in the same direction as the horizon, right? That's what horizontal means. So after you let go of the ball, no more force is accelerating it forward, so its horizontal velocity is constant if you ignore air resistance. But we know air resistance occurs, so we know that the net force is going to push back on it, so eventually it's going to slow down, right? Mm-hmm. But if there was no air resistance, we would move at a constant velocity, and the ball would technically never stop, right? But we know that doesn't happen. So what else do you think is affecting it besides air resistance? Gravity, because we know projectiles move in a curved path. So even if you throw something up, eventually it starts to come back down. Why? Due to gravity. Okay, so gravity accelerates it downward, so not only is it moving in the horizontal direction, it is also moving down in a vertical direction. Gravity exerts an unbalanced force on the ball, changing the direction of its paths from only forward to both forward and down. That's why we have a curved path. The result is that the ball appears to travel in a curve, even though its horizontal and vertical motions are completely independent of each other. There's that word independent again. What does that mean? Okay, independent of each other means that its vertical motion is going on all by itself, and its horizontal motion is going on all by itself. They happen to be going on at the same time, but one has nothing to do with the other. Okay, its horizontal motion is being caused by you applying a force to the ball, correct? Its vertical motion is being caused by gravity's pull down on it, so that's another force. So two independent forces, they just happen to be happening at the exact same time. Okay, so let's look at an example, right? So we have a ball. We are standing at the top of a cliff. Okay, the first person A takes the ball and it just drops it. So a ball thrown and a ball dropped are going to hit the ground at the same time. Why? Because technically they are undergoing the same vertical force. Because I just said those two forces are going to act independent of one another. So one being dropped is going to have the same vertical force being acted on it of gravity, right? One being thrown is still having the same vertical force acting on it, gravity. The only difference is they're going to land at different spots because one of them has a horizontal force where the other one doesn't, but they're independent of each other, so the vertical force of gravity pulling down on it will make them hit the ground at the exact same time, regardless of if they are thrown and or dropped. Okay, so let's talk about some roller coasters a little bit. You guys did a lab yesterday on the computer where you got to manipulate parts on a roller coaster to see how the acceleration and the forces changed, right? So when an object changes its velocity, it has a change in acceleration. So just like when you have a ball going around a curve, the change in the direction of the velocity is towards the center of the curve. So this is kind of like if any of you have ever driven a race car around a track, we all know that when we get to the curves, they start to drift, right? Because they're changing velocity, they're changing direction, therefore, but they're being drawn towards the center of the track. Okay, acceleration towards the center of a curve is called centripetal acceleration. When a ball has centripetal acceleration, the direction of the force on the ball also must be towards the center of the curve. And the force exerted towards the center of the curved path is called your centripetal force. So if you look at the picture, we have a picture of a roller coaster. So for any of you who are super curious about how roller coasters work, this is how they work. So in the center of a circle, I'm going to put a star. And around in this circle, we have the roller coaster. Now, inertia is when an object's wanting to resist change, right? So right now, we have a person sitting in the roller coaster, and I'm going to draw a stick person because I can't draw. We have a person sitting in the roller coaster, and at this point in the curve, his inertia is pulling him this direction. Right now, because at any point in time, you're traveling in a straight line. You don't really ever travel in a curve. Okay, so at this point in time, he is traveling in this direction, so he wants to stay in that direction. However, due to gravity and the idea of centripetal force, since he is being moved in a circular path, he's actually also being pulled towards the center, and that's called your centripetal force. So that is actually what is keeping him in the car, is that centripetal force. Even because his inertia, his body wants to continue to travel in that same. So whoever designs roller coasters has to make sure your speed is enough for your centripetal force to overcome your inertia. See, don't you guys feel smart now? Yeah. Okay, so what we're going to do now is we are going to look at a few questions. This is a little bit of review over Newton's first laws and gravity. So kind of the notes we've taken over the last few days. So let's see if we can answer some of these questions, because you guys all know that my questions, my homework questions, have a way of making their way onto the test, don't they? Mm-hmm. So let's see if we can answer some of these questions. So let's look at number 1. Every object in the universe exerts a force on every other object. This force is called gravity, right? Haven't we just spent the last 30 minutes talking about gravity? Mm-hmm. Okay, so number 2. The measure of the gravitational force exerted by Earth on an object is the object's, we have weight or mass. We're talking about a force, so it's probably going to be weight, right? Mass is the same regardless of where you go. Mass is part of Newton's second law equation, force equals mass times acceleration, right? But weight is a force, correct? Because weight takes into account both your mass and your acceleration. So number 2, we're looking for a gravitational force. So it can't be mass, because mass has nothing to do with acceleration. So we are looking for weight. Hey, number 3. The amount of gravitational force between two objects depends on their what? Mass and distance. So if I was looking at this question on the test, I would be thinking, Miss Tackett's crazy. She hasn't mentioned color one time this entire unit. So that's kind of an easy cross out, correct? All right, let's look at number 4. Number 4 says, weight is measured in units called newtons, because again, weight is a force. Force in this class, as of right now, is measured in newtons. Number 5, the greater an object's length, the stronger the gravitational force. So, remember, gravity is affected by 2 things, distance and mass. So which one of those is my options? A, mass. Velocity has nothing to do with your gravitational pull. Number 6, mass is measured in units called grams and kilograms. So again, I'm testing your knowledge on the difference between mass and weight here, aren't I? Okay, number 7, a weight reading on a scale shows the what type of something exerted by the scale? Right, when you stand on the scale, you are measuring gravitational pull on you. Gravity is working down, so we're looking for a downward force, right? Number 8, Earth exerts a stronger gravitational force than the moon because Earth has more mass. Number 9, the masses on your hand and your notebook are quite small, so the force of attraction between them is... Anyone want to take a guess? I actually haven't given this to you on a silver platter yet. Everything has, if you have mass, you have an attractive force. But it has your hand and a textbook has a very small mass, right? So it's going to be a weak force. Is there still a force there? Yeah. Yes, but it's very small because the mass is very small. And then the last one, an object transported from the surface of Earth to the surface of the moon has its weight decrease because you have a smaller gravitational pull, so your force is going to decrease.